What if I told you the smallest, most distant world in our solar system holds secrets that defy everything we thought we knew? Pluto, once the ninth planet, now labeled a dwarf, is far more than just a frozen rock at the edge of darkness. Its icy surface hides cracks deeper than the Grand Canyon, mountains taller than Everest, and a heart-shaped glacier the size of Texas that might be hiding an underground ocean. This tiny world, barely visible from Earth, punches far above its weight when it comes to mysteries. Think about this. When New Horizons flew by Pluto in 2015, scientists expected a dead, cratered ball of ice. Instead, they found a world alive with bizarre geological activity, dunes made of methane sand, glaciers that flow like wax, and a sky that glows blue despite being 40 times farther from the sun than Earth. How is any of this possible, and why does Pluto, a world smaller than our moon, have such a complex and chaotic atmosphere that it snows nitrogen at altitudes higher than jets fly on Earth? The more we learn, the less Pluto makes sense. That's the thing about this distant underdog, it refuses to be ignored. From its controversial demotion to the mind-bending discoveries that followed, Pluto has always kept us guessing. And today, we're diving deep into the 25 most baffling enigmas this little world has thrown at us. We'll explore icy volcanoes that might still be active, a wobbling orbit that defies physics, and the chilling possibility that Pluto's underground ocean could harbor the ingredients for life. So buckle up, because by the time we're done, you'll see why this so-called dwarf planet might just be the solar system's most fascinating world. That massive heart-shaped region on Pluto, called Tombaugh Regio after the astronomer who discovered the planet, isn't just a cosmic coincidence, it's one of the solar system's strangest geological puzzles. Stretching over 1,000 miles wide, this bright, glacier-filled basin looks like it was painted onto Pluto's surface with impossibly crisp edges. But here's what baffles scientists. While the rest of Pluto is scarred with craters and ancient terrain, this heart appears eerily smooth, as if something is constantly erasing its flaws. The secret lies in what it's made of, not water ice like Earth's glaciers, but frozen nitrogen, carbon monoxide, and methane. These exotic ices behave unlike anything on our planet. During Pluto's long, elliptical orbit, trace amounts of sunlight vaporize the nitrogen, creating an ultra-thin atmosphere that eventually snows back down, resurfacing the heart in a slow, otherworldly cycle. But that doesn't explain everything. Why is the western half of the heart, called Sputnik Planitia, so perfectly reflective? Some researchers think an underground liquid ocean might be flexing Pluto's crust, keeping this area unnaturally flat. Others speculate that the basin is a colossal impact crater, its depths trapping ice like a cosmic bowl. Even more bizarre, the heart seems to be alive. Images from New Horizons show cellular patterns in the ice, almost like a boiling pot of liquid nitrogen slowly churning under the surface. And the way it's positioned directly opposite Pluto's largest moon, Charon hints that this feature might actually be controlling the dwarf planet's orientation, like a counterweight in space. So while it looks like a valentine from the cosmos, Tombaugh Regio could be the key to understanding why tiny Pluto, against all odds, remains one of the most geologically active worlds at the edge of our solar system. Picture an alien landscape where entire mountains glide across frozen plains like icebergs in a slow-motion sea. That's exactly what's happening in Pluto's Sputnik Planitia, the western lobe of its heart-shaped basin. Here, clusters of water ice hills, some as tall as skyscrapers, float atop a vast, convecting ocean of solid nitrogen. It's a geological phenomenon unlike anything on Earth. These aren't just stationary features. Radar and imagery from New Horizons revealed that the hills drift over time, carried by the sluggish flow of nitrogen ice beneath them. Imagine an ice cube bobbing in a glass of water, except the glass is 500 miles wide, the ice is -390 degrees Fahrenheit, and that liquid is actually a frozen solid moving like thick syrup. That's the surreal reality of Pluto's floating hills. What makes them even stranger is their composition. While most of Pluto's surface is coated in volatile ices like nitrogen and methane, these hills are made of rigid water ice, hard as rock at such frigid temperatures. Scientists think they might be fragments of Pluto's ancient crust, shattered by impacts and left to wander like cosmic icebergs. Others propose they're cryovolcanic in origin, spewed up from beneath the surface by long-dead ice volcanoes. Either way, their existence hints at layers of history frozen in time, but the real mystery is their movement. On Earth, glaciers flow downhill under gravity's pull. On Pluto, the nitrogen ice in Sputnik Planitia churns in massive, convection-driven cells. Think of a lava lamp, but with slabs of ice rising and sinking over centuries. The hill's hitch rides on these slow-motion currents, sometimes clustering like driftwood at the edges of convective cells. Some even leave trails behind them, etching scars in the nitrogen like cosmic footprints. The strangest part, this whole system might be active right now. Pluto's weak sunlight shouldn't provide enough energy to power such dynamic geology, yet the lack of impact craters on Sputnik Planitia suggests the surface is being constantly renewed. If these hills are still moving, it means Pluto, billions of miles from the Sun, is somehow generating enough heat to keep its frozen heart beating. Pluto's atmosphere shouldn't even exist. At its distance from the Sun, gases should freeze solid and collapse onto the surface, yet somehow, this dwarf planet defies the odds with a hazy, ever-changing sky that operates like nothing else in our solar system. Imagine an air so thin it's barely there, yet so dynamic it expands and contracts like a cosmic lung with no discernible rhythm. When New Horizons zipped past in 2015, it found an atmosphere nearly 1,000 miles high, 10 times thicker than predicted, with layers of blue haze and winds that reverse direction unpredictably. The driving force behind this chaos, nitrogen. Pluto's surface is laced with frozen nitrogen, and when even a sliver of sunlight touches it, the ice skips the liquid phase entirely, transforming directly into gas through sublimation. This process should follow predictable seasonal patterns, but Pluto's seasons are anything but normal. Its 248-year orbit is so elongated that some seasons last decades longer than others, while its extreme axial tilt creates wild temperature swings. The result, an atmosphere that balloons when Pluto nears the Sun, then partially vanishes as it retreats, except sometimes it doesn't. In 2016, just a year after New Horizons' visit, astronomers watched in disbelief as Pluto's atmospheric pressure inexplicably doubled despite moving farther from the Sun. What's really baffling is the haze. High-altitude hydrocarbons scatter sunlight into a perpetual twilight glow, creating stunning blue layers that shouldn't persist in such a sparse atmosphere. Some scientists think cosmic rays or ultraviolet light trigger chemical reactions up there, while others speculate that microscopic ice crystals are acting like celestial mirrors. But the biggest mystery lies beneath the surface, hidden nitrogen reservoirs. Pluto's dramatic atmospheric swings hint at vast, undiscovered underground stores of gas that burp into the sky when least expected. Could cracks in the ice or cryovolcanoes be releasing pressurized pockets? Or is Sputnik Planitia that heart-shaped glacier acting as a planetary pressure valve, regulating the atmosphere like a cosmic thermostat? The more we study Pluto's sky, the less it obeys the rules. Current climate models fail to predict its behavior, leaving scientists to wonder if they're missing a fundamental piece of physics. One thing's certain, this tiny world with its ghostly, pulsing atmosphere continues to rewrite the textbooks on planetary science. If you think Pluto's floating hills are strange, wait until you see the blades. Stretching across a region called Tartarus Dorsa, these jagged ridges soar hundreds of feet into the sky, their razor-sharp peaks glinting with methane ice under the dim sunlight. Picture a frozen forest of colossal knives, their edges so precise they look almost artificial. Yet they're entirely natural, sculpted by conditions so extreme they defy earthly logic. Scientists call this the bladed terrain, and it's one of Pluto's most alien landscapes. The ridges, some spaced as evenly as skyscraper blocks in a city grid, run for hundreds of miles, their formation a puzzle wrapped in layers of ice. The leading theory, sublimation, where sunlight transforms solid methane directly into gas, leaving behind skeletal structures of more durable ice. Imagine carving a block of dry ice with a heat lamp, watching it crumble into spines as the softer parts vanish. Now scale that up to planetary proportions, with methane ice eroding over millions of years under a sun that's barely more than a bright star. But here's where it gets controversial. Some researchers argue wind might play a role despite Pluto's whisper-thin atmosphere. They point to the ridge's uniform alignment, suggesting gusts, however faint, could be sandblasting the ice into these eerie formations. Others propose tectonic forces, with Pluto's crust buckling under stress to create fractures that later erode into blades. The wildest idea: these could be ancient dunes, frozen in time when Pluto's atmosphere was thicker. Their once shifting sands now cemented into place by eons of ultra-cold temperatures. The sheer scale of these structures adds to the mystery. On Earth, wind and water shape features over centuries. On Pluto, where time moves at a glacial pace literally, these blades likely took tens of millions of years to form, yet they look startlingly fresh with few craters marring their surfaces. That raises a chilling possibility. Could this process still be active today? If so, Pluto isn't just a relic of the solar system's past. It's a world still writing its own geological story, one razor-sharp ridge at a time. Pluto's surface isn't just dotted with ordinary mountains. It's home to what might be some of the most bizarre volcanoes in the solar system. Towering over the landscape, Right Mons rises nearly 3 miles high, with a sprawling depression at its summit that looks eerily like a volcanic caldera. But instead of spewing molten rock, this giant could be erupting slushy mixtures of water ice, ammonia, and nitrogen in slow-motion explosions. Welcome to the cryptic world of cryovolcanoes, where geology defies everything we know about volcanic activity. The strangest part: there's no obvious sign of recent eruptions, no fresh flows, no plumes of icy particles, just a hulking, wrinkled structure that seems frozen in time. If Right Mons is active, why doesn't it leave trails? One theory suggests these eruptions happen in ultra-slow motion, oozing out over centuries like chilled syrup. Another possibility is that the erupted material vaporizes instantly in Pluto's thin atmosphere, leaving no trace behind. Or worse, what if we're witnessing a cryovolcano that's already dead, its secrets locked beneath layers of ancient ice? That raises the biggest question of all: where's the heat coming from? Pluto is too small and distant to retain much internal warmth from its formation, and tidal forces from its moon Charon aren't strong enough to generate significant friction. Yet the lack of impact craters on Right Mons hints at a surface that's been resurfaced relatively recently, at least in geological terms. Some scientists point to radioactive decay in Pluto's core as a possible energy source, while others speculate that pockets of antifreeze like ammonia could lower the melting point of ice, allowing sluggish eruptions even in extreme cold. Then there's the wild card: an underground ocean. If liquid water exists beneath Pluto's crust, as some data suggests, its movement could create enough pressure to force icy sludge to the surface through cracks. Imagine a frozen version of Earth's geysers, erupting not with boiling water, but with a bizarre slurry that flash freezes in the vacuum of space. Whether active or extinct, Pluto's cryovolcanoes challenge our understanding of how geology works in the farthest reaches of the solar system, and hint that even tiny worlds can harbor fiery secrets beneath their icy shells. Deep within Pluto's Cthulhu macula, a sprawling, dark region named after H.P. Lovecraft's cosmic horror, lies one of the dwarf planet's most unsettling enigmas: vast, streaky stains that crawl across the landscape like shadows refusing to fade. These aren't mere patches of darkened ice. They're dynamic, finger-like marks stretching hundreds of miles, their origins tangled in a web of cosmic chemistry and planetary mystery. The first clue to their identity comes from their color. Pluto's reddish-brown tint has long been blamed on Tholen's complex organic molecules formed when methane and nitrogen are zapped by solar radiation over millions of years. But Cthulhu Macula's streaks are darker and more concentrated than anywhere else, suggesting something far more potent is at work. Some scientists argue these could be deposits of primordial carbon, baked into the surface by ancient impacts or even cryovolcanic activity. Others propose their radiation scars, left behind as cosmic rays stripped away lighter elements, leaving behind a tar-like residue akin to the dark side of Saturn's moon Iapetus. What makes these streaks truly bizarre is their behavior. Unlike static impact craters or frozen plains, some appear to follow topographical contours, snaking around mountains and pooling in valleys as if flowing like liquid. Yet Pluto's surface is far too cold for any conventional liquid to exist. Could they be evidence of seasonal changes where brief bursts of sunlight vaporize volatile ices, leaving behind dark organic sludge? Or perhaps they're the remnants of underground reservoirs that briefly breach the surface like ink bleeding through paper. The wildest theory connects them to Pluto's atmosphere. When the dwarf planet's nitrogen sky collapses during its decades-long winters, could hydrocarbons literally rain down, staining the ice like cosmic graffiti? New Horizons detected a haze of soot-like particles high above Pluto material that might eventually settle and weave these cryptic patterns. Whatever the answer, one thing's clear: these streaks aren't just stains. They're a record of Pluto's hidden chemistry, written in a language we're only beginning to decipher. And locked within their darkness might be clues to how organic compounds, the building blocks of life, scatter across the frozen edges of our solar system. Pluto doesn't spin like a typical planet. It wobbles, dances, and shares its orbit with its largest moon, Charon, in a gravitational tug of war so extreme that the center of their rotation lies in empty space. This isn't just a quirky detail, it's a cosmic balancing act that defies conventional planet-moon relationships. Earth and our moon orbit a point deep within Earth's core, but Pluto and Charon are so close in mass that they whirl around a shared point between them, like two figure skaters holding hands and spinning midair. Scientists call this a binary system, and it's the only known case in our solar system where a moon holds enough sway to redefine its host's motion. The consequences of this dance are written all over Pluto's surface. Because Charon's gravity locks one side of Pluto in a perpetual stare, a phenomenon called tidal locking, the dwarf planet's rotation has been yanked into sync over billions of years. But here's where it gets chaotic. This gravitational wrestling match doesn't just stop at rotation. Some researchers suspect it could be warping Pluto's very shape, squeezing its interior like a stress ball and fueling the geological activity we see today. Those massive cracks sprawling across its surface, the heart-shaped glacier that refuses to erode, they might all be scars from this relentless cosmic tug of war. Even more intriguing is the heat generated by this interaction. Tidal forces from Charon could be flexing Pluto's icy shell, creating friction that keeps subsurface oceans liquid far longer than expected. Imagine bending a paperclip back and forth until it grows warm. Now scale that up to planetary proportions with an entire world's crust grinding against itself. This might explain why Pluto, a tiny frozen rock at the edge of the solar system, has glaciers that flow and mountains that float. The energy has to come from somewhere, and Charon's relentless pull could be the hidden engine. But the biggest question remains: is this binary dance still reshaping Pluto today? Some models suggest the two bodies could be driving each other into ever stranger configurations, with Charon's orbit slowly expanding as Pluto's spin continues to adjust. If true, it means Pluto isn't just a static relic of the solar system's past. It's a world still evolving under the influence of its own moon, rewriting the rules of what we thought possible in the frigid depths of space. The absence of craters on parts of Pluto's surface isn't just odd, it's a cosmic detective story. Take Sputnik Planitia, that sprawling nitrogen glacier shaped like half a heart. Compared to the pockmarked terrain elsewhere on Pluto, this region is eerily smooth, with barely a scratch to show for its 4.5 billion years of existence. If this were any other icy world in the outer solar system, it should look like Swiss cheese from relentless asteroid impacts. So where did all the craters go? One possibility is that Sputnik Planitia is essentially a giant ice skating rink with a self-healing surface. The nitrogen ice here behaves less like solid ground and more like a slow-moving fluid creeping forward at a glacial pace, literally. Over time, fresh ice wells up from below, covering old impact scars as effortlessly as new snow blankets footprints in a blizzard. But this theory has a catch. Even flowing nitrogen ice shouldn't erase craters this efficiently. That's led some scientists to propose something far more dramatic, a massive upheaval in Pluto's recent geological past. Imagine an entire section of the dwarf planet's crust turning itself inside out, with ancient terrain sinking beneath newer ice like a planetary facelift. Then there's the heat question. For Sputnik Planitia to stay this pristine, Pluto's interior might still be churning with unexpected energy. Radioactive elements decaying in its core could be generating just enough warmth to keep the nitrogen ice mobile, while tidal forces from Charon's gravity flex the crust like putty. Some researchers even speculate that an underground ocean, if it exists, could be transferring heat upward, creating pockets of slushy instability that erase surface scars over millennia. But the most tantalizing clue lies in the numbers. Crater counts suggest parts of Sputnik Planitia could be as young as 10 million years, a blink in cosmic time. To put that in perspective, Earth's dinosaurs went extinct 65 million years ago. If Pluto's surface is really this fresh, it means this tiny world wasn't just geologically active in the distant past, it might still be rewriting its own surface today. That raises an even bigger mystery. What invisible engine is powering Pluto's youthful glow at the edge of the solar system's deep freeze? Pluto's atmosphere isn't just thin, it's a breathtaking light show. When New Horizons looked back at the dwarf planet after its flyby, it captured something surreal. A glowing blue halo surrounding Pluto, split into 20 distinct layers of haze stretching 500 miles high. These shimmering veils shouldn't exist at all. At Pluto's distance, sunlight is nearly 2,000 times weaker than on Earth, barely enough to power chemical reactions, let alone create such an elaborate atmospheric display. Yet there they were, glowing like suspended ocean waves frozen in twilight. The secret lies in methane. As sunlight fractures these molecules high above Pluto's surface, they recombine into heavier hydrocarbons like ethylene and acetylene. Think of it as cosmic alchemy turning simple gas into complex soot. These particles eventually clump together, growing just heavy enough to drift downward while still catching the light. But here's the puzzle. Simple diffusion should make this haze smooth and uniform, not stacked in precise layers like a celestial wedding cake. Something is corralling these particles into bands with mathematical precision, and scientists are torn between two radical explanations. The first involves gravity waves, not to be confused with gravitational waves from black holes. As Pluto's frigid air slides over mountains or churns with temperature changes, it could create ripples in the atmosphere, much like waves forming behind a boat. These undulations might act as invisible shelves, trapping haze particles at specific altitudes. The second theory is even stranger. The layers could be fingerprints of hidden frost volcanoes. If cryovolcanic plumes are injecting fresh gas into the atmosphere at regular intervals, each eruption might seed a new haze layer like rings in a tree trunk. But the real shocker is the color. That ethereal blue tint comes from the way sunlight scatters off the haze particles, the same phenomenon that makes Earth's sky appear blue. The difference: our atmosphere scatters nitrogen and oxygen, while Pluto's does it with tar-like organic compounds. These tholins, as they're called, are the same molecules that paint Pluto's surface reddish-brown. Up in the atmosphere, they act like billions of tiny prisms, bending sunlight into that haunting cerulean glow. What nobody expected was how dynamic this system is. Some haze layers shift dramatically over short periods, while others vanish entirely during Pluto's decades-long seasons. New Horizons even spotted what looked like haze, clouds, filmy patches suspended in the layers, possibly condensed from fresh methane bursts. If confirmed, these would be the first true clouds ever seen on a dwarf planet, proving that even at the solar system's edge, weather finds a way. The deeper we look, the more Pluto's atmosphere resembles a living thing, breathing, pulsing, and painting its own sky with chemistry we're only beginning to understand. One of Pluto's most visually striking mysteries lies in a region called Tartarus Dorsa, where the landscape transforms into something straight out of a science fiction nightmare. A vast expanse of jagged, overlapping ridges that look eerily like reptilian scales. Dubbed the snakeskin terrain, this bizarre formation covers hundreds of miles with patterns so precise they seem almost artificial. Each scale-like blade rises hundreds of feet, their edges sharp as shattered glass, glinting with methane ice under the faint sunlight. It's a sight so alien that even seasoned planetary scientists initially struggled to believe it was natural. The prevailing theory points to methane's volatile nature on Pluto. At temperatures hovering around -390 degrees Fahrenheit, methane behaves unlike anything on Earth. During Pluto's fleeting, warmer seasons, if you can call them that, trace sunlight causes methane ice to sublimate directly into gas, bypassing the liquid phase entirely. Over millennia, this cycle might carve the ice into these jagged formations, leaving behind hardened ridges where the methane resists erosion. Imagine a block of dry ice left to evaporate unevenly, its surface crumbling into spines. Except here, the process unfolds across an entire world, sculpting landscapes at a geological pace. But there's a problem with this explanation. The snakeskin terrain's patterns are too regular. Sublimation alone shouldn't create such uniform, repeating ridges, especially not with the razor-sharp symmetry seen in New Horizons images. Some researchers propose that Pluto's extreme temperature swings varying by dozens of degrees over its eccentric orbit could be driving a feedback loop where methane freezes, fractures, and sublimates in rhythmic cycles. Others wonder if wind, despite Pluto's wispy atmosphere, might be rearranging ice particles into dunes that later cement into these jagged forms. The wildest hypothesis involves cryovolcanism. If subterranean heat occasionally melts pockets of methane-rich ice, the resulting slush could erupt onto the surface, flash freezing into brittle sheets that later crack under stress. Picture a frozen lake fracturing into plates, except on Pluto. Those plates might then be etched by sublimation into the scales we see today. Yet even this doesn't fully account for the terrain's eerie organization. What truly stumps scientists is the sheer freshness of the snakeskin. Unlike Pluto's cratered highlands, this region shows few signs of impacts, suggesting it's geologically young, possibly reshaped within the last few million years. That raises a provocative question: could this process still be happening? If so, Pluto isn't just a frozen relic. It's a world where exotic ices are still writing their own cryptic patterns into the landscape, one sublimation cycle at a time. Until another mission visits, Tartarus Dorsa's reptilian enigma remains one of the solar system's most haunting geological puzzles. Pluto's North Pole wears a rusty crown, a sprawling red cap so vivid it stands out against the dwarf planet's otherwise pale and mottled surface. This isn't just a splash of color. It's a colossal laboratory where cosmic chemistry transforms simple ices into complex organic compounds called tholins. These molecules, forged when methane and nitrogen are bombarded by solar radiation over millennia, paint Pluto's pole in shades of burnt umber and brick red. But here's the catch: while tholins exist across Pluto, they're concentrated here in a way that defies simple explanation. Why does this one region hoard them like treasure? The process starts with Pluto's thin atmosphere. At the poles, where sunlight strikes at oblique angles for decades at a time, methane molecules rise high enough to be cracked apart by ultraviolet radiation. The fragments then recombine into heavier, more complex hydrocarbons, a process akin to cosmic cooking, where radiation acts as the chef, slow roasting simple ingredients into a thick organic haze. Eventually, these particles snow down, staining the ice below. But this doesn't account for the cap's stark borders or its uneven texture. On other worlds with tholin-coated surfaces, like Saturn's moon Titan, the distribution is more uniform. Pluto's cap, by contrast, has patchy swirls and sharp edges, as if an invisible hand brushed pigment onto only certain sections. Weather might hold the key. Pluto's wispy atmosphere, though barely there, could be channeling tholin-rich winds toward the pole like a slow-motion conveyor belt. During the dwarf planet's long summer, when the North Pole is bathed in continuous, albeit faint, sunlight, sublimating nitrogen ice might create microclimates, tiny pockets of atmospheric circulation that deposit tholins in specific patterns. Another theory suggests seasonal frost cycles are at work. As temperatures fluctuate over Pluto's 248-year orbit, some areas might accumulate tholins while others lose them to sublimation or chemical breakdown. Then there's the wild card: topography. The polar region's elevation and terrain could be trapping tholins like a cosmic bowl, preventing them from spreading evenly. New Horizons spotted valleys and pits near the cap's edge features that might act as wind barriers or cold traps, corralling the reddish particles into concentrated zones. Even more intriguing is the possibility of ancient cryovolcanic activity. If eruptions once spewed organic, rich sludge at the pole, lingering heat or chemical residue could be attracting tholin buildup like a magnet. The red cap's true significance lies in what it represents: a frozen record of chemistry that might seed the building blocks of life. Tholins are rich in carbon and nitrogen, essential ingredients for amino acids. While Pluto itself is too cold for life as we know it, these compounds could be raining down on other, warmer worlds in the Kuiper belt, delivering raw materials for prebiotic chemistry. The cap isn't just a curiosity, it's a time capsule preserving the recipe for how complexity emerges in the universe's most frigid corners. And until we land a probe on Pluto's surface, its rusty hues will keep whispering secrets about how the solar system paints its darkest canvases. Pluto flips the laws of atmospheric physics on their head with a temperature profile that baffles scientists. While most planets, including Earth, get colder as you rise through their atmospheres, Pluto does the exact opposite. Its upper atmosphere hovers around -290 degrees Fahrenheit, warmer than the surface at a bone-chilling -390. This inverted temperature gradient shouldn't exist on a world so small and distant, yet New Horizons instruments confirmed it with unmistakable clarity. The secret lies in an anti-greenhouse effect. On Earth, greenhouse gases like carbon dioxide trap heat near the surface, creating a familiar warmth. Pluto's version works in reverse. Gases like hydrogen cyanide, yes, the same toxic compound used in laboratories, act as a planetary coolant, absorbing infrared radiation and re-emitting it into space before it can warm the surface. But higher up, solar ultraviolet light directly energizes methane and nitrogen molecules, giving the upper atmosphere an unexpected thermal boost. It's as if the dwarf planet wrapped itself in a thermal blanket, but accidentally put it on upside down. What makes this phenomenon even stranger is its uniqueness. Other icy bodies in the Kuiper belt, like Eris or Makemake, lack this inverted temperature structure. The key difference might be Pluto's dynamic atmosphere. Unlike its frozen neighbors, Pluto's nitrogen-rich air expands and contracts dramatically over its 248-year orbit, creating layers where gases interact in unexpected ways. Hydrogen cyanide, though present only in trace amounts, could be acting as a thermostat, absorbing just enough heat to warm the upper layers while letting the surface languish in deep cold. The real mystery is how this delicate balance persists. Pluto's atmosphere should have collapsed entirely when it moved farther from the Sun in the 1990s, yet it clung to existence, even developing this bizarre thermal inversion. Some researchers speculate that seasonal changes in ice sublimation keep pumping fresh gas into the system, while others point to undiscovered chemistry involving complex hydrocarbons. One radical theory suggests cosmic rays, high-energy particles from deep space, are ionizing the atmosphere, creating pockets of warmth through electrical friction. This thermal quirk does more than just defy expectations. It rewrites the rulebook for planetary atmospheres. If a tiny, frozen world like Pluto can sustain such an unexpected heat distribution, what other atmospheric anomalies might lurk in the far reaches of the solar system? Every new discovery suggests that even in the coldest, darkest corners of space, nature finds ways to surprise us. Beneath Pluto's dim sunlight, something impossible is happening. Rivers of nitrogen ice, miles wide and hundreds of feet thick, are creeping across Sputnik Planitia like slow-motion lava. These aren't your typical glaciers. On Earth, frozen water grinds downhill over centuries, shaped by gravity and seasons. But Pluto's glaciers are made of nitrogen, an ice so exotic it flows like honey in a deep freezer, sculpting valleys and ridges in conditions colder than liquid air. The most striking feature is a network of branching channels etched into the ice, resembling dried-up riverbeds from an aerial photo. Scientists call them fluted terrain, and they tell a story of movement. Nitrogen ice, soft and pliable even at -390 degrees Fahrenheit, oozes around obstacles, carving zigzagging paths that look freshly made. Some flows stretch over 100 miles, their edges crisp as if drawn with a knife. What's shocking is their youth. Crater counts suggest these glaciers could be mere millions of years old, practically newborn in geological time. How does a world this frigid sustain such dynamic geology? The answer might lie in a bizarre property of nitrogen ice. Unlike water ice, which stays brittle at Pluto's temperatures, nitrogen ice undergoes something called thermal creep. Even the faintest warmth, say, from a sun that appears only as a bright star, can make its crystalline structure rearrange, allowing it to flow like wax under minuscule pressure. Combine that with convection currents churning beneath Sputnik Planitia's surface, and you've got a recipe for glaciers that never stop moving. But here's the catch: thermal creep alone shouldn't produce flows this vigorous. On Pluto, where the sun's energy is barely a whisper, something else must be greasing the wheels. Some researchers point to dissolved carbon monoxide or methane lowering the ice's viscosity, effectively turning it into a super slippery slurry. Others suspect tidal heating from Charon's gravitational pull is flexing Pluto's crust, creating just enough warmth to keep the nitrogen malleable. The most tantalizing theory involves radioactive decay deep underground. Potassium and uranium isotopes decaying in Pluto's rocky core might be leaking heat upward, turning Sputnik Planitia into a slow-motion ice rink with an invisible radiator below. The strangest clue comes from the glacier's behavior. They don't just flow, they surge, accelerating in sudden bursts that leave behind chaotic swirls and fractured plains. On Earth, glacial surges happen when meltwater lubricates the base, but on Pluto, there's no liquid nitrogen to play that role. Unless, and this is where it gets wild, pockets of pressurized nitrogen gas are building up beneath the ice, periodically bursting through like a frozen geyser, sending glaciers skidding across the landscape. Every observation leads to more questions. Why do some glaciers appear stalled, their fronts towering like frozen waves mid-collapse? Are there seasons in this icy ballet, with flows speeding up when Pluto's eccentric orbit brings it fractionally closer to the Sun? And if these glaciers are still active today, what does that say about the fate of Pluto's heart-shaped basin? One thing's certain: this tiny world, once written off as a dead ice ball, is teaching us that even at the solar system's edge, the ground beneath our feet, or in this case beneath a spacecraft's camera, is anything but still. Amidst the chaos of Pluto's fractured terrain, one feature stands out like a cosmic signature: an unmistakable X carved into the ice, discovered in high-resolution New Horizons images of the Vega Terra region. This perfect cruciform shape spans nearly 40 miles across, its arms intersecting at crisp right angles. At first glance, it looks almost artificial, like a deliberate mark left by some unseen force. But the truth behind this formation is even stranger than fiction. The leading theory suggests this X is a rare convergence of tectonic fractures, a snapshot of Pluto's crust screaming under stress. Imagine two sets of parallel faults, each running in opposite directions, overlapping at just the right moment to form this geometric anomaly. The same phenomenon happens on Earth when seismic activity creates intersecting cracks, but Pluto's version is frozen in time, preserved by temperatures so cold that even tectonic scars never fade. Yet there's a problem. The X appears startlingly fresh, with no debris filling its grooves or craters dimpling its surface. That suggests these cracks might have formed recently, or that something is actively keeping them clean. But tectonic forces alone can't fully explain the X's precision. On other worlds with similar fracturing, like Jupiter's moon Europa, intersecting cracks rarely produce such flawless symmetry. Some researchers propose an alternative explanation. The X might be an optical illusion created by overlapping glacial flows. Picture two rivers of nitrogen ice creeping across the landscape at oblique angles, their edges eroding into sharp ridges that happen to align into this uncanny shape. The shadows cast by Pluto's low sun could then enhance the illusion, making the X pop against the surrounding terrain. The biggest mystery isn't just how it formed, it's why we've only found one. If tectonic stress or glacial flows commonly create X-shaped features, they should litter Pluto's surface. Instead, this stands alone, a solitary enigma in a world already overflowing with oddities. Could it mark the epicenter of some ancient impact, with radial fractures converging at this exact spot? Or is it a fleeting alignment destined to vanish as Pluto's surface continues to shift over millennia? One tantalizing clue comes from its surroundings. The X sits at the edge of a vast, dimpled plain called basket terrain, a patchwork of hexagon-shaped depressions that resemble a cosmic beehive. Some scientists think these hexagons formed through sublimation, where sunlight vaporizes ice unevenly, leaving behind geometric scars. If so, the X might be a transitional feature, caught between two competing geological processes, one breaking the crust, the other dissolving it. Until another probe visits Pluto, this celestial X will remain a riddle. Whether it's a tectonic crossroads, a trick of the light, or something even more unexpected, it serves as a reminder that even at the solar system's edge, nature loves to leave behind puzzles waiting to be solved. And for now, that crisp, perfect mark keeps its secrets locked in ice. Near Pluto's equator, a cluster of dark spots sprawls across the landscape like a fleet of shadowy islands adrift on a pale, frozen sea. Each one spans up to 30 miles wide, large enough to swallow entire cities, yet they cling together in a loose formation, defying the chaos of the dwarf planet's otherwise fractured terrain. These aren't random blemishes. Their arrangement is too deliberate, their edges too crisp. New Horizons captured them in stunning detail, but their origins remain one of Pluto's most persistent riddles. The first clue lies in their composition. spectroscopic data suggests the spots are rich in complex organic molecules, likely tholins, the same reddish-brown compounds that stain other parts of Pluto. But here, the material is darker and more concentrated, as if something amplified their formation. One theory points to cryovolcanic activity. Ancient ice vents might have spewed sooty plumes that settled in these precise patches. Another possibility involves wind. Despite Pluto's wispy atmosphere, some models suggest breezes could organize dark particles into dunes or drifts, though no one expected them to create such defined circular features. Then there's the spacing. The spots aren't scattered randomly, they're grouped like continents on a planetary scale archipelago. This pattern hints at underlying geology, perhaps fractures in Pluto's crust that released gases or darker material in periodic bursts. Similar clusters appear near tectonic boundaries on Earth, where volcanic vents line up along fault lines. But Pluto's spots show no obvious cracks or ridges beneath them, leaving researchers to wonder if invisible forces like convection currents in the ice are guiding their placement. The most tantalizing detail, their stability. On a world where nitrogen glaciers flow and methane ice sublimates into seasonal haze, these spots have stubbornly resisted change. Years of observation show no significant shifts in their size or position. Whatever cements them in place, whether a subsurface glue of tar like organics or some gravitational anchor, it's strong enough to withstand Pluto's dynamic surface. Yet the biggest mystery isn't just how they formed, but why they're here. Equatorial regions on most planets receive the most sunlight, which should bake away volatile compounds. Instead, these spots thrive, almost as if they're feeding off the energy. Some scientists speculate they could be called traps, topographic lows where dark material accumulates and lingers like coffee stains in the bottom of a cup. Others propose a darker twist. Maybe they're sinkholes collapsing into hidden caverns left by long-vanished nitrogen lakes. One thing's certain, these enigmatic stains are more than just surface quirks. They're windows into Pluto's hidden chemistry, a chemistry that might be brewing complex molecules right under our noses. And until another mission ventures to this distant world, their secrets will remain as inscrutable as the dark spots themselves. Pluto's atmosphere is vanishing before our eyes, but not in the way anyone expected. As the dwarf planet retreats from the Sun on its eccentric 248-year orbit, its tenuous nitrogen sky should be freezing solid and collapsing onto the surface like a deflating balloon. Yet year after year, telescopes catch glimpses of a stubborn atmosphere clinging to existence, refusing to follow the rules. In 2016, just as Pluto reached its farthest point from the Sun, astronomers watched in shock as its atmospheric pressure doubled, a cosmic paradox that still has scientists scrambling for explanations. The culprit might be thermal inertia, a delayed reaction to sunlight stored in Pluto's icy heart. Imagine baking a potato, then pulling it from the oven. It keeps radiating heat long after removal. Similarly, Sputnik Planitia's vast nitrogen glacier could be acting like a planetary battery, slowly releasing stored warmth even as Pluto moves into its deep freeze. But here's the twist. Calculations suggest this reservoir shouldn't hold enough heat to delay atmospheric collapse by more than a decade. Yet Pluto's sky persists, hinting at hidden nitrogen reserves lurking beneath the surface like subterranean lakes of gas, periodically venting to recharge the atmosphere. Another theory points to Charon's gravitational influence. As Pluto's binary partner tugs on its icy shell, the friction might generate just enough heat to keep nitrogen sublimating in fits and starts. Or perhaps cryovolcanoes are erupting frozen nitrogen like geysers, injecting fresh gas into the system. The wildest idea, Pluto's dark equatorial patches, those sprawling organic stains, could be absorbing sunlight like solar panels, locally warming the ice and creating microclimates that outpace global cooling. The stakes are high for future missions. If Pluto's atmosphere collapses entirely, surface features could change dramatically, glaciers might stop flowing, haze layers could vanish and any remaining volatile ices would lock into permanent hibernation. But if it stabilizes at a thin whisper, we might witness something unprecedented, a dwarf planet cycling between atmospheric boom and bust over millennia. Right now, every observation suggests Pluto is dancing to its own rhythm, rewriting the textbook on how small, distant worlds breathe. And with no follow-up mission en route, we're left watching from billions of miles away, piecing together clues from a disappearing act that defies all expectations. Pluto's Viking terror looks like something a dragon might call home, a sprawling badlands of overlapping, scaly ridges that rise hundreds of feet into the dim sunlight, their edges sharp as shattered glass. Dubbed the dragon scales, these formations stretch for hundreds of miles, each ridge curving and crashing into its neighbor like frozen waves in a storm. At first glance, they resemble Earth's mountain ranges, but their origins are anything but familiar. These aren't ordinary peaks carved by erosion or volcanic activity. Instead, they appear to be the result of Pluto's crust buckling under unimaginable stress. Like the wrinkles on a shrinking apple, the scales might have formed as the dwarf planet's interior cooled over billions of years, causing the surface to contract and fracture. But here's the twist: these ridges aren't random. They align in eerily consistent patterns, suggesting something deeper and far more chaotic is at work beneath the ice. One leading theory points to tidal forces. Pluto's dance with Charon creates gravitational tug-of-wars that flex the dwarf planet's crust, potentially cracking it into these segmented ridges. Another idea involves volatile ices like methane and nitrogen expanding and contracting with temperature swings, slowly pushing the terrain into these overlapping folds. Imagine leaving a plastic bottle in the freezer. The material warps as it cools. Now picture that same process, but on a planetary scale, with ice as hard as steel crumpling like paper. What baffles scientists most is the scale's precision. Unlike Earth's mountains, which wear their age in weathered slopes and eroded peaks, Pluto's dragon scales look freshly forged. Some ridges even gleam with methane frost, as if they're still actively shifting. Could tectonic stresses still be reshaping Viking terror today, or are we seeing the aftermath of a cataclysmic event, an ancient impact or a sudden collapse of subterranean caverns that left these scars behind? Even more perplexing is their sheer size. Some ridges run uninterrupted for dozens of miles, their crests sharp enough to cast shadows that stretch like claws across the landscape. If these are Pluto's version of mountain ranges, they're unlike any we've seen elsewhere in the solar system. On Earth, mountains grow through continental collisions or volcanic buildup. On Mars, they're carved by wind and ancient lava flows. But Pluto's scales seem to defy comparison, a geological fingerprint unique to this tiny, distant world. The dragon scales may hold clues to Pluto's fiery past. If subsurface oceans once sloshed beneath this ice, their freezing could have warped the crust into these jagged formations. Or perhaps the ridges mark the boundaries of ancient plates, evidence that Pluto, against all odds, once harbored its own version of plate tectonics. Until another mission ventures to this frozen frontier, these serrated landscapes will keep their secrets, a reminder that even in the darkest corners of space, nature's creativity knows no bounds. When New Horizons flew through the Pluto system in 2015, scientists braced for a hazard they never encountered: cosmic dust. Out here in the Kuiper belt, where countless icy fragments collide and crumble, planets like Pluto should be shrouded in a permanent haze of debris. Yet the spacecraft's instruments detected something startling: almost nothing. The space around Pluto was eerily clean, as if someone had swept away every speck of dust. This wasn't just unexpected, it defied everything we know about how small, icy worlds behave at the solar system's edge. Compare this to other Kuiper belt objects. Saturn's rings constantly grind ice into powder. Comets like Churyumov-Gerasimen co-spew dust clouds as they heat up. even Pluto's neighbor, Haumea, shows signs of a dusty halo from surface impacts. But Pluto, it's spotless. This raises a glaring question. Where did all the debris go? One possibility is that Pluto's wispy atmosphere acts like a cosmic broom. Nitrogen and methane gas escaping into space might collide with dust particles, dragging them down to the surface through a process called aerodynamic drag. Think of it like snowflakes sticking to a wet windshield, only here, the windshield is Pluto's gravity and the snowflakes are microscopic space dust. But there's a catch. This theory works only if Pluto's atmosphere is dense enough to trap dust, and right now, it's barely there. That's why some researchers suspect something more exotic is at play, like electrostatic forces. Pluto's surface, bombarded by solar radiation, could be generating electric fields strong enough to repel dust particles, flinging them away like magnets pushing against each other. Or perhaps the dust is simply hiding in plain sight. New Horizons spotted vast glaciers of nitrogen ice on Pluto's surface, ice so slippery and mobile it might be swallowing dust like quicks and burying evidence of impacts before craters can form. The most tantalizing clue comes from Charon. Pluto's largest moon also lacks dust, but its surface is coated in a thin layer of ammonia, a compound that breaks down when exposed to radiation. Some scientists think this ammonia could be acting like cosmic glue, capturing dust particles and chemically bonding them to the surface. If so, Pluto might be doing the same on a planetary scale, its volatile ices acting like a giant lint roller for space debris. The implications are staggering. If Pluto really is self-cleaning, it challenges our understanding of how small worlds evolve. Most Kuiper belt objects are thought to be dusty relics, unchanged since the solar system's birth. But Pluto, with its dynamic geology and vanishing atmosphere, might be actively rewriting its own history, erasing impact scars, smoothing its surface, and presenting itself as a world frozen in time when, in reality, it's anything but. Until another mission ventures this far out, the mystery of Pluto's missing dust will linger, a silent testament to how much we still have to learn about the solar system's darkest corners. Scattered across Pluto's frozen plains, some craters wear glowing halos like celestial crowns, bright, luminous rings that stand out against the darker terrain. These aren't just simple impact scars, they're enigmas wrapped in ice, hinting at secrets buried beneath the surface. When New Horizons spotted these ghostly rings, scientists immediately noticed their odd duality. Some craters had them, while others nearby, seemingly identical in size and age, did not. So what's turning these cosmic pockmarks into radiant beacons at the edge of the solar system? The most striking examples lie in Pluto's Viking Terror, where certain craters gleam with halos up to twice as bright as their surroundings. One leading explanation points to upwelling ice, a process where impacts fracture Pluto's crust, exposing purer water ice from below. Unlike the darker, tholin-stained surface, this freshly exposed ice reflects sunlight like a mirror, creating those eerie rings. But this theory hits a snub. If impacts simply uncovered existing ice, why don't all craters glow? Some researchers speculate that only impacts powerful enough to crack through an insulating layer of darker material reach the bright ice beneath. Others think these halos might mark spots where subsurface heat mobilized ice flows long after the initial collision, like frozen lava seeping into fractures. Then there's the wild card, volatile ices. Pluto's surface is a patchwork of nitrogen, methane, and carbon monoxide, each with different reflective properties. When an impact vaporizes these ices, they might recondense in unique patterns, creating temporary bright rings that fade over millennia. The halos we see today could be the remnants of this process, like frost lingering in the shadow of a boulder long after sunrise. But this doesn't explain their persistence. If volatile ices were responsible, sunlight should have darkened them by now, unless something, maybe residual geothermal heat, is actively maintaining their brightness. The plot thickens when you examine their distribution. These halos aren't random, they cluster in specific regions, often near tectonic faults or glacier boundaries. That alignment suggests a deeper connection to Pluto's internal activity. Could cryovolcanic vents be channeling fresh ice to the surface along these fractures, creating permanent bright zones where impacts later occur? Or do the halos mark spots where Pluto's underground ocean, if it exists, once seeped through the crust, leaving behind salt deposits that boost reflectivity? The most tantalizing clue comes from their edges. Unlike typical impact ejector blankets which fade gradually, these halos have razor-sharp boundaries, as if someone traced them with a cosmic highlighter. That precision hints at an ongoing process, something actively maintaining the contrast between bright and dark terrain. Whether it's seasonal frost cycles, lingering geothermal activity, or some unseen chemical reaction, one thing's clear: these radiant rings are more than just scars. They're neon signs pointing to Pluto's hidden vitality, proving that even in the deepest freeze, this world refuses to sit still. And until we land a probe on its surface, their glow will keep whispering questions we can't yet answer. The winds of Pluto whisper secrets in the icy darkness, secrets written in sprawling dunes of methane sand that stretch across the Cthulhu macula like alien hieroglyphs. These aren't your typical desert dunes. Instead of golden silica, they're sculpted from frozen methane grains, each no larger than a grain of sugar, piled into waves that rise hundreds of feet high. The sheer existence of these dunes is a paradox. Pluto's atmosphere is 100,000 times thinner than Earth's, so wispy you'd struggle to feel a breeze if you stood on its surface. Yet here, in this frozen wasteland, winds somehow muster enough strength to carve and move entire landscapes. How? The answer might lie in Pluto's extreme conditions. At -390 degrees Fahrenheit, methane ice becomes as hard as rock, but when even a sliver of sunlight touches it, the surface warms just enough for microscopic grains to break free. In such thin air, escaping gases from sublimating ice could act like turbocharged winds, lofting particles in brief, violent bursts. Think of dry ice skittering across a lab table, except here, the table is a planet and the skittering lasts for centuries. New Horizons spotted these dunes nestled between mountain ranges, their crescent shapes suggesting winds blow in consistent directions despite Pluto's chaotic atmosphere. But simple sublimation might not be the whole story. Some researchers propose electrostatic forces are at play. As sunlight ionizes methane grains, they could repel each other like magnets, hopping across the surface in a process called saltation. Others point to thermal tides, subtle atmospheric expansions and contractions caused by the sun's faint heat, that might generate just enough breeze to keep the dunes marching. The wildest theory involves Pluto's nitrogen heart, Sputnik Planitia. As its glaciers churn, they could be pumping nitrogen gas into the atmosphere, creating seasonal wind patterns powerful enough to sculpt dunes but too fleeting for us to observe directly. The dunes arrangement deepens the mystery. They cluster in sheltered zones, often near mountain foothills or crater rims, as if the terrain itself is funneling unseen gusts. Some dunes even overlap in intricate crosshatched patterns, hinting at shifting wind directions over millennia. Yet their sharp crests suggest recent activity, geologically speaking. If these dunes are still on the move, it means Pluto's whisper-thin air harbors forces we've barely begun to understand. Perhaps the most haunting question isn't how these dunes exist, but what they're made of. Methane shouldn't survive long on Pluto's surface without replenishment. Cosmic radiation should break it down, yet the dunes appear fresh, almost pristine. Could hidden reservoirs of methane ice be venting gas like subterranean geysers? Or are we witnessing the slow-motion collapse of an ancient methane layer, its grains eroding into these surreal formations? Either way, these dunes are more than just fossils of past winds. They're proof that even in the solar system's quietest corners, the ground beneath our feet is never truly still. Stretching across Pluto's battered surface like a frozen explosion, the spider fractures of Sleipnir fossa form one of the solar system's most hauntingly symmetrical features. This sprawling network of radial cracks fans out with near-geometric precision, some veins extending over 300 miles from a central point, as if something beneath the ice pressed upward with such force that the crust splintered like glass. But what could create such a perfect, web-like pattern on a world where geology supposedly ground to a halt billions of years ago? The fracture's knife-edged ridges suggest violence frozen in time. On most planets, radial cracks like these typically stem from meteor impacts or volcanic uplift. Yet Sleipnir fossa shows no telltale crater at its center, no collapsed caldera to explain the stress. Instead, scientists are left with two controversial theories. The first points to cryovolcanism, a slow-motion eruption of slushy water ice mixed with ammonia or methanol that oozed upward, fracturing the overlying nitrogen crust like a hydraulic jack. The second proposes something far stranger, a subterranean nitrogen lake that froze, expanded, and literally pushed the surface apart from below. Picture an ice cube cracking a plastic tray in your freezer, only here, the tray is Pluto's crust and the ice cube is the size of a small country. What defies logic is the spider's symmetry. Natural fractures tend to follow weaknesses in rock, creating jagged, uneven patterns. But Sleipnir's arms branch at eerily consistent angles, their spacing so uniform it looks almost engineered. Some researchers think Pluto's unique ice composition holds the key. Nitrogen and methane ices dominant in this region behave unlike Earth's rigid crustal rocks. When stressed, they might fracture in mathematically predictable ways, like a sheet of frozen rubber snapping along clean lines. Others propose tidal forces from Charon could be tuning these fractures like guitar strings, their gravitational resonance creating patterns too precise for random geology. The darkest mystery lurks beneath the ice. Thermal scans from New Horizons revealed subtle warmth radiating from some fractures, hinting that whatever formed them might still be active. If true, Pluto isn't just a relic of the solar system's birth. It's a world where unseen forces continue to scribe cryptic messages into the ice, each fracture a whisper from depths we may never reach. And as sunlight glints off those razor-edged crevices, they stand as frozen testament to a simple truth. Even in the void's coldest corners, pressure always finds a way out. Pluto's ice caps aren't frozen in time, they're playing a slow-motion game of planetary musical chairs. Observations dating back to the 1980s show stark differences in the size and location of these bright, reflective regions compared to modern images from New Horizons. The North Polar Cap, once a dominant feature, appears to be shrinking while frosty deposits have sprouted in new, unexpected places near the equator. This isn't just random weather, it's evidence of a world where ice migrates on a scale that would dwarf Earth's glacial epochs. The driving force behind this icy wanderlust lies in Pluto's extreme seasons. With an orbit so elongated it swings from 30 to nearly 50 times Earth's distance from the Sun, and an axial tilt of 120 degrees that practically rolls it on its side, Pluto experiences seasons that last decades. During its summer, when one pole tilts sunward for over a century at a time, volatile ices like nitrogen and methane sublimate into the atmosphere, only to snow back down at the opposite pole during the long winter. But here's what's bizarre, the caps aren't shifting symmetrically. Infrared scans reveal some frost deposits are lagging behind, as if Pluto's climate has memory holding onto cold spots long after they should have vanished. The speed of this migration is equally puzzling. While Earth's ice ages unfold over millennia, Pluto's caps appear to reorganize within mere centuries. Calculations based on New Horizons data suggest some frost zones are creeping poleward at rates of several inches per year, fast enough that a hypothetical observer could witness noticeable changes within a human lifetime. This breakneck pace points to Pluto's exotic ices behaving like nothing on Earth. Nitrogen glaciers, for instance, might flow like wax under minuscule pressure, while methane frost could hopscotch across the surface through seasonal winds or electrostatic levitation. The wild card in this icy ballet is Sputnik Planitia, that heart-shaped nitrogen sea. Some models suggest its massive gravitational pull, yes, a glacier so heavy it affects Pluto's balance, could be yanking the entire planet's climate system out of alignment. As nitrogen evaporates from one hemisphere and condenses in the other, the weight redistribution might be tilting Pluto's axis like a wobbly top, accelerating the ice cap's movement. This creates a feedback loop. More tilt means more extreme seasons, which drives faster ice migration, which further destabilizes the spin. If true, Pluto isn't just passively reacting to orbital changes, it's actively reshaping itself in real time. The most haunting question isn't where the ice is going, but what's left behind. Dark, tholin-stained patches mark former frost zones like ghostly footprints, their organic, rich residues resisting refrosting even as temperatures drop. These climate scars suggest Pluto's surface has a long-term memory, with some areas chemically altered to repel ice for millennia. It's a reminder that even at the solar system's edge, change is the only constant, and that Pluto's frozen face is far more dynamic than its quiet, sunless skies would ever let on. Among Pluto's countless mysteries, few are as visually striking as the unexplained bright spots, glowing patches of ice that shine like cosmic beacons against the dwarf planet's otherwise muted palette. These aren't just slightly reflective areas, they're dazzlingly bright, some appearing almost fluorescent in New Horizons images, as if someone had dropped spotlights onto the frozen surface. The strangest part, they're isolated, often sitting in the middle of featureless plains or tucked between dark, tholin-stained ridges with no obvious geological connection. Unlike the vast, self-renewing glaciers of Sputnik Planitia, these spots seem to defy the rules of aging, remaining stubbornly pristine in a world where sunlight and cosmic radiation should have darkened them eons ago. One cluster of these luminous patches sits in the middle of Pluto's Badlands, a region scarred by tectonic fractures and chaotic terrain. Their brightness suggests they're made of water ice, the most reflective substance on Pluto, but water ice should be buried beneath layers of nitrogen and methane frost. So how did these patches end up on the surface, untouched by the chemical stew that stains the rest of the planet? The leading theory points to cryovolcanism. If geysers or icy plumes erupted here, they could have spewed super clean water ice from deep underground, leaving behind these radiant scars. Imagine a frozen version of Yellowstone's geysers, but instead of hot water, they're blasting slushy, ammonia-rich slurries that freeze instantly in the vacuum of space. But there's a problem with this idea. Most cryovolcanic features elsewhere in the solar system, like those on Neptune's moon Triton or Saturn's Enceladus, leave behind obvious vents or fissures. Pluto's bright spots show no such structures, no cracks, no ridges, no depression to mark an eruption site. That's led some researchers to propose an even wilder explanation. These patches might be cold traps, topographic lows where water ice migrates over millennia. On Pluto, where temperatures vary wildly across its eccentric orbit, water molecules could hop across the surface like cosmic breadcrumbs, eventually collecting in these bright oases. It's a process seen on Earth's moon, where ice accumulates in permanently shadowed craters, except here, it's happening in broad daylight. The real enigma is their longevity. Tholins, the dark organic molecules that paint most of Pluto's surface reddish-brown, should eventually coat these spots, dimming their shine. Yet they persist, gleaming like they were formed yesterday. One possibility is that they're actively being refreshed, either by micro-eruptions too subtle for New Horizons to detect or by some kind of electrostatic levitation that keeps dark particles from settling. Another theory suggests these patches might be laced with antifreeze compounds like ammonia or methanol. which lower the melting point of ice and prevent chemical reactions with tholins. The most tantalizing clue comes from their distribution. These bright spots aren't scattered randomly. They cluster near regions with suspected subsurface activity, like Sputnik Planitia's glacial currents or the spider-like fractures of Sleipnir fossa. That proximity hints at a hidden connection, perhaps pockets of residual heat or underground liquid water seeping through cracks and resurfacing in these radiant bursts. If so, Pluto's bright spots aren't just static anomalies. They could be flashing signals of a world that's still geologically alive, whispering secrets from beneath its frozen shell. And until another mission ventures to this distant frontier, their brilliance will keep challenging everything we thought we knew about how small, cold worlds evolve. Pluto's surface holds a network of jagged, luminous ridges that crack across the landscape like bolts of frozen lightning, a geological puzzle so intricate it makes even seasoned planetary scientists pause. These zigzagging formations, best seen in regions like Vega Terra, slice through the ice with surgical precision, their paths neither random nor fully predictable. Some stretch uninterrupted for miles, branching and merging in patterns that mirror lightning strikes captured in slow motion. But these aren't electrical scars, they are fractures in Pluto's icy shell, forged by forces we're only beginning to unravel. The conventional explanation points to thermal contraction, the idea that Pluto's crust cracked as it cooled over billions of years, like mud drying in the sun. On other worlds, such fractures often form neat grids or parallel lines, but Pluto's frozen lightning defies simplicity. Its ridges intersect at chaotic angles, some curving abruptly as if diverted by invisible barriers. This suggests something beyond gradual cooling. One compelling theory involves tidal stresses from Charon, Pluto's binary companion. The gravitational tug of war between the two bodies could be twisting Pluto's crust like a twisting rubber ball, creating fractures that propagate in these frenzied, branching patterns. Another clue lies in the ridge's composition. Spectral data reveals they're rich in water ice, harder than steel at Pluto's temperatures, and dusted with methane frost that makes them gleam against darker terrain. This combination hints at a dynamic process, perhaps liquid water once welled up from below, filling the cracks before freezing into these permanent scars. But liquid water on Pluto, that would require internal heat sources far beyond what a small, icy world should retain. Unless, and this is where it gets, speculative radioactive decay or residual formation heat is still warming Pluto's depths, creating pockets of slush that occasionally surge upward. The most baffling aspect is their youth. Many of these ridges crosscut fresh glacial plains and show minimal erosion, suggesting they formed recently, or that Pluto's surface is far more active than we imagined. Some fractures even appear to glow brighter than their surroundings, as if they're lined with fresher, purer ice exposed by ongoing tectonic shifts. Could these lightning bolts be evidence of present-day geological activity, with Pluto's crust still cracking under stress? Then there's the outlier theory, electrostatic forces. Pluto's surface, bombarded by solar wind, builds up electric charges that might discharge along weak points in the ice, etching these jagged paths over millennia. It's a stretch, but not impossible after all. Lightning does carve similar fractal patterns on Earth, just in milliseconds rather than eons. Whether the answer lies in forgotten oceans, tidal tremors, or something even stranger, one thing's clear: Pluto's frozen lightning is more than a geological curiosity. It's a snapshot of a world caught between forces we've yet to fully measure, where even the cracks in the ice tell a story we're only starting to read. Pluto's 5 moons don't just orbit, they tumble through space like drunken acrobats, defying every expectation of celestial order. Charon, the largest, locks Pluto in their gravitational dance, but the smaller moons, Styx, Nix, Kerberos, and Hydra, spin wildly, their rotations so chaotic that if you stood on one, the sun might rise in the west one day and the north the next. Hydra somersaults end over end every 10 hours while Nix flips unpredictably, as if shoved by invisible hands. These aren't the sedate, synchronized orbits of most moons. They're evidence of a system still reeling from cosmic violence. The leading theory points to a cataclysmic collision, a younger Pluto smashing into another Kuiper belt object, scattering debris that later clumped into these misshapen moons. That's why they're riddled with bizarre proportions. Hydra looks like a stretched rubber band, while Nix resembles a squashed football. Their surfaces reflect sunlight at absurdly different angles, suggesting they're coated in a patchwork of ice and dark organic material like poorly mixed paint. But the real shocker, their orbits resonate with Charon in precise ratios. Hydra circles Pluto 3 times for every 2 of Nix's orbits, a delicate gravitational harmony amid the chaos. This delicate balance hints at hidden forces. Some researchers suspect undiscovered mass lurking in Pluto's system, perhaps a long-lost moon that shattered and left debris behind, or even a slight asymmetry in Pluto's own gravity field tugging the moons off kilter. Others propose that Charon's gravity acts like a cosmic drumbeat, destabilizing the smaller moons over eons through a process called chaotic rotation. Imagine a parent swinging a child by the arms. The child's legs flail unpredictably, just like Nix and Hydra's spins. What's truly unsettling is how young these orbits seem. Computer simulations show the moons should have stabilized by now, unless something, maybe residual gas in Pluto's atmosphere or gravitational nudges from passing Kuiper belt objects, keeps kicking them off course. If true, it means Pluto's moon system isn't a fossil of the past but a dynamic, ever-evolving puzzle where chaos isn't a bug, it's a feature. And until another mission peers into this gravitational whirlwind, the moon's disorder will keep challenging our understanding of how celestial families behave at the solar system's edge. Pluto has spent decades being dismissed as a frozen, lifeless rock at the edge of our solar system. But the truth couldn't be more different. From heart-shaped glaciers hiding underground oceans to nitrogen rivers carving valleys in slow motion, this tiny world has rewritten the rulebook on what's possible. We thought we'd find a cratered relic of the solar system's birth. Instead, we discovered a geologically active enigma, pulsing with mysteries that challenge everything we know about small, distant worlds. Take Pluto's atmosphere, a hazy, ever-changing sky that glows blue despite being thinner than a whisper, or those towering snakeskin ridges, sharp as shattered glass, that stretch for hundreds of miles like reptilian scales frozen in time. And who could forget the floating hills of water ice, drifting like cosmic icebergs atop a sea of solid nitrogen? Each discovery peels back another layer, revealing just how little we truly understand. What's most thrilling isn't just what we've found, it's how much remains hidden. Is Sputnik Planitia's heart-shaped basin covering a sloshing underground ocean? Could cryovolcanoes still be oozing icy sludge onto the surface today? And why does Pluto's atmosphere stubbornly cling to existence, doubling in pressure when it should be collapsing? These aren't just academic questions, they're clues to how small worlds generate heat, evolve over time, and maybe, just maybe, create conditions ripe for chemistry that could spark life elsewhere in the cosmos. The next chapter of Pluto's story is already being written. Missions like NASA's proposed Persephone orbiter aim to map its hidden oceans, while next-generation telescopes could sniff out atmospheric changes in real time. One day, a lander might even touch down on those icy plains, melting through the surface to probe the secrets beneath. Until then, Pluto will keep whispering its riddles across the void, daring us to look closer. So what's your favorite Pluto mystery? The glowing X etched into its ice, the dunes of methane sand sculpted by impossible winds? Drop your thoughts in the comments, and if you're as obsessed with space's unsolved puzzles as we are, hit subscribe to explore more cosmic enigmas. Because one thing's certain, the universe's weirdest stories are always hiding where we least expect them.